So we try to find out the characteristic equation. Characteristic equation can be found out by using the K-map S R Q. Now to find out characteristic equation, which is 0 0 0 1 1 1 1 0 0 1. So we can write it down as R bar Q bar R bar Q R Q R Q bar. So it will be S bar S. So as we can see, Q plus, or the current out or the future output, is high for 1 2 4 1 4 5, and these are 2. So we write it as 1. It is low for 2 3. It is high for 4. It is high for 5, and 6 and 7 are don't care. So we often consider it. So let's take this 1 and this. Okay. So the characteristic equation for SR is given by S plus R bar Q. This is the characteristic equation for S plus R bar Q. Now let's start with the D flip-flop. What is a D flip-flop? D flip-flop is actually a flip-flop which is having a single input D data. That is, when D is high, S becomes high, as we can see from the circuit, and R becomes low since it is passed on with a NOT gate. Similarly, when D is low, S becomes 0 and R becomes 1, so we get the output as reset state. The above is the circuit for a positive edge triggered D flip-flop. So before moving on further, let's study the working of D flip-flop and the characteristic tables and characteristic equation for D flip-flop. As this is the circuit diagram, this is a truth table. So we'll draw again the truth table of the D flip-flop. First of all, to find the characteristic table and characteristic equation. Characteristic table for D flip-flops. So first step is start with the truth table. D Q plus. When D is 0, output is 0. When D is 1, output is 1. This is the truth table for it. Now second is draw the characteristic table. D Q Q plus. Say 0 0 0 1 1 0 1 1. When D is 0 0, D is 0, again it is 0. When D is 1, Q plus is 1. D is 1, Q plus is 1. This is the characteristic table for D flip-flops. So now let's find out the characteristic equation. Characteristic equation for D flip-flops. D Q Q plus. Say Q Q plus will be zeros. D, sorry, it will be D and Q. So it is high for 0 1. You can see 2 and 3. 2 and 3. So the characteristic equation, one it will be D bar D. This will be Q bar Q. So the characteristic equation for D flip-flop is D Q bar plus DQ. The application of D flip-flop. The parallel data transfer, that is, D flip-flop can be used to transfer the data parallelly, to transfer the logic circuit outputs X, Y, Z to flip-flops Q1, Q2, Q3 for storage. Now, for better understanding and other applications, we can also find the excitation table for D flip-flop. The procedure for finding the excitation table for D flip-flop is very much similar, like the way we have found out the characteristic table or the characteristic equations. So the excitation table for D flip-flop can be found out. Excitation table is given as Q plus D 0 0 0 1 1 0 1 1. The excitation table for D flip-flop is this. So let's take on JK flip-flops. JK flip-flops are those flip-flops which have the same structure like SR flip-flop, but the only difference and the advantage of JK flip-flop is that it doesn't have an invalid state, how the SR flip-flop had for 0 0 using NOR and for 1 1 using NAND. So the JK flip-flop here is free of invalid states. Let's study in detail how the JK flip-flop works. JK flip-flop includes a toggle state. That is, when J is equal to high and K equal to low, we get it as a set state. When K equal to high, J equal to low, we get it as a reset state. When both the inputs are low, we get it as no change, similar to SR flip-flop. And when both the inputs are high, we get a toggle state. Therefore, that is, the output continuously keeps on toggling. Unlike in SR flip-flop, where both the inputs high were given as an invalid state. So let's take on the truth table for the JK flip-flop. As we can see, when J is equal to 0, Q equal to K equal to 0, the output is no change. The above is a circuit diagram for JK flip-flop, which has a pulse detection circuit to detect the rising or the falling edge of the flip-flops. This part is called as a basic NAND latch. You can say NOR latch, a simple latch we can say that. So it doesn't have this. This is a pulse detection circuit. That is, when J is equal to 0, K is equal to 0, we get the output as 0, no change. When 0 and 1, we get the output as reset. When 1 and 0, we get the output as set. And 1 1, here we get the toggle. That's it. Now this equation is called as the characteristic equation, which is the. So I'll definitely show you how this equation comes from. Characteristic equation, which comes from this. So to work out on how this characteristic equations comes from, or where does this characteristic equation comes from, let's see the working of the JK flip-flops. So to find out the characteristic equation, characteristic table and characteristic equation for JK flip-flops. Let's start first with the truth table for JK flip-flop. JK Q plus. Okay. So 0 0 0 1 1 0 1 1. The output is 0 or hold state. 0 1 gives 0 set state, reset state. 1 0 gives 1, which is a set state, and 1 1 is a toggle state. That is, suppose if the previous output is 0, the current or the next output will be 1, and vice versa is what the toggle state is called. Okay, so this is the truth table. Now let's find out the characteristic table. Characteristic table consists of J, K, the current output, and the future output. Q plus. So let's have 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we can check out from this. We group this to find the characteristic equations. 0 and 0, it shows hold set, that is 0 and 1 previous values. 0 and 1 will give 0 0, 1 1, and 1 1 again will give the toggle state. That is, here it is 0, therefore the current output will be 1. Here it is 1, therefore the current output will be 0. This is what the toggle state is. So if we write the K map, J K, this will be J K Q 0 0 0 1 1 1 1 0 0 1. That is, the output is high for 1 4 5 6. Okay, so we'll write down 1 4 4 5 6 4 5 6. This should not be. So we'll find out, we'll group the two ones in the form of twos. So after finding or after sorting it out, we get it as characteristic equation is equal to j q bar plus k bar q is the characteristic equation